Hello dear students, glad to meet you again in this last session of this chapter 1, some basic concepts of chemistry. In this session 1.14, we are going to discuss balancing of redox reactions in grade 11. In session 1.1, we have discussed about some importance of chemistry, nature of matter and its classification. In session 1.2, we have discussed the 7 basic units of SI system. In session 1.3, we have discussed the physical quantitative properties of matter. In session 1.4, we have discussed the uncertainty in measurements. In session 1.5, we have discussed the laws of chemical combination. In session 1.6, we have discussed the postulates of Dalton's atomic theory, atomic mass, molecular mass, and formula mass. In session 1.7, we discussed mole concept, Avogadro number, molar mass, and molar volume. In session 1.8, we have discussed gram equivalent mass for oxidizing and reducing agent and for acids and base. Session 1.9, we discussed the molecular and empirical formula. In session 1.10, we discussed stoichiometry and its calculations. In session 1.11, we have discussed the methods to express the concentrations in chemical solutions. In session 1.12, we have discussed the classical concept and electronic concept of redox reactions, and we have discussed how to compute the oxidation number of an element. In session 1.13, we have discussed types of redox reactions. Learning outcomes. Students, at the end of this session, you will be able to list 2 different types of balanced redox reactions, formulate a balanced redox reaction from 2 half reactions. Balancing redox reaction. The 2 methods for balancing the redox reaction are the oxidation number method and ion electron method or half reaction method. As we know that redox reaction is based on the number of electrons, these 2 methods for balancing the redox reaction is based on the principle that the total number of electrons donated by the reducing agent is equal to the total number of electrons gained by the oxidizing agent. Oxidation number method. In this method, the number of electrons lost or gained in the reaction is calculated from the oxidation number of elements before and after the reaction. Let us consider the reaction between ferrous sulfate and potassium permanganate in acid medium. Before balancing this redox reaction using oxidation number method, let us calculate the oxidation numbers of elements before and after the reaction. Since this reaction between ferrous sulfate and potassium permanganate takes place in the presence of acid medium, we have ferrous sulfate, potassium permanganate, and sulfuric acid in the reactant side. And we have ferric sulfate, manganese sulfate, potassium sulfate, and water in the product side. First, let us find out the oxidation number of the reactants and the oxidation number of the products in this reaction. Already we have seen how to calculate the oxidation number of a compound having 3 different elements. We have to separate all the 3 elements, and the first element in the compound is a positive element and the last element in a compound is a negative element and the in-between element is a positive element. To find the oxidation number of Fe in FeSO4, let us assume the oxidation number of Fe as X. So X plus oxidation number of sulfur is plus 6 plus we have 4 oxygen. So 4 into oxidation number of oxygen is minus 2 equal to 0, because we know that the algebraic sum of the oxidation number of all the atoms in a molecule equal to 0. So X plus 6, 4 into minus 2 is minus 8 is equal to 0. This gives the value X equal to plus 2, which is the oxidation number of iron in ferrous sulfate. To find out the oxidation number of Mn in KMnO4, let us assume the oxidation number of Mn as X. We know that the oxidation number of the alkali metal, that is potassium, is 1. So 1 plus, we have 1 Mn, so X plus, and we have 4 oxygen, so 4 into minus 2, which is the oxidation number of oxygen, is equal to 0. So 1 plus X, 4 into minus 2, minus 8 equal to 0. Therefore, X equal to plus 7, which is the oxidation number of Mn in KMnO4. Coming to the product side, first let us find out the oxidation number of Fe in Fe2SO4 thrice. Let us assume the oxidation number of Fe as X. We have 2 Fe, so 2X plus, we have 3 sulfur because this 3 is common to sulfur and oxygen. So 3 into plus 6, which is the oxidation number of sulfur, plus this 4 into 3, 12. So we have 12 oxygen. So 12 into oxidation number of oxygen is minus 2 is equal to 0. So 2X, 3 into 6 plus 18, 12 into minus 2 is minus 24 equal to 0. So 2x equal to 6. This gives the value for x as plus 3, which is the oxidation number of Fe in Fe2SO4 thrice. Now coming to Mn in MnSO4. Let us assume the oxidation number of Mn as X. Mn plus oxidation number of sulfur is 6. So plus 6 plus, we have 4 oxygen. So 4 into minus 2 equal to 0. So X plus 6, 4 into minus 2 is minus 8 equal to 0. So this gives the value of X as plus 2, which is the oxidation number of Mn in MnSO4. Already we know the oxidation number of the elements present in ferrous sulfate and potassium permanganate. Now let us find out the oxidation number of sulfur in sulfuric acid in the reactant side. Let us assume the oxidation number of sulfur as X. We have 2 hydrogens, so 2 into 1, which is the oxidation number of hydrogen plus X plus, and we have 4 oxygen, so 4 into minus 2 is equal to 0, because we know that the algebraic sum of the oxidation number of all the atoms present in a molecule is equal to 0. So 2 into 1, 2 plus X, 4 into minus 2 is minus 8 is equal to 0, which gives the value of X is equal to plus 6, which is the oxidation number of sulfur in sulfuric acid. Coming to the product side, we know the oxidation numbers of elements present in ferric sulfate and manganese sulfate. Now let us find out the oxidation number of sulfur in potassium sulfate. Assume the oxidation number of sulfur as X. So we have 2 potassium here. So 2 into 1, because we know that the oxidation number of the alkali metal potassium is 1, plus X plus, we have 4 oxygen. So 4 into minus 2 is equal to 0. So 2 into 1, 2 plus X, 4 into minus 2, minus 8 is equal to 0. So this gives the value of X as plus 6 for sulfur in potassium sulfate. And we know the oxidation number of hydrogen is plus 1 and the oxidation number of oxygen is minus 2 in water molecule. Now let us write the oxidation number of elements of reactants and products of this reaction. Ferrous sulfate oxidation number plus 2. Sulfur oxidation number plus 3 throughout this reaction. Oxygen oxidation number minus 2 throughout this reaction. And the alkali metal potassium has the oxidation number plus 1 throughout this reaction. Coming to manganese, it is plus 7 in potassium permanganate, but it is plus 2 in the case of manganese sulfate. So in the first step to balance the redox reaction using oxidation number method, we need to use the oxidation number concept to identify the reactants, that is the atoms, which undergo oxidation and reduction in this unbalanced equation. Now, when you note this unbalanced redox reaction, we could see the oxidation number of iron in ferrous sulfate is plus 2 and the oxidation number of iron in ferric sulfate is plus 3. Here the oxidation number increases from plus 2 to plus 3. So this is the oxidation part of this redox reaction. Coming to potassium permanganate, the oxidation number of Mn in KMnO4 is plus 7 and the oxidation number of Mn in MnSO4 is plus 2. Here the oxidation number decreases. So this is the reduction part of this redox reaction. In step 2, we have to equate the number of electrons and cross multiply with suitable integer. Here, Fe2 plus in FeSO4 loses 1 electron and becomes Fe3 plus in Fe2SO4 thrice. In this reaction, it loses 1 electron. So the number of electron lost by 1 iron atom is 1. If you notice the number of Fe in the right hand side, we have 2Fe in Fe2SO4 thrice, but in the left hand side we have 1 Fe. To balance the number of Fe in this reaction, we need to write the coefficient 2 in front of FeSO4. We know that 1 Fe from FeSO4 loses 1 electron during oxidation reaction. Now we have 2 Fe in FeSO4. So it loses 2 electron during this oxidation reaction. Now coming to potassium permanganate, plus 7 Mn in KMnO4 gains 5 electron and becomes plus 2 in MnSO4. To equate the number of electrons in the oxidation reaction with the number of electrons in the reduction reaction, we need to multiply this oxidation reaction by 5 and the reduction reaction by 2. In step 3, let us balance the oxidized and the reduced part of the reaction. So the oxidation part of the reaction is 2FeSO4 gives Fe2SO4, and the reduction part of the reaction is KMnO4 gives MnSO4. Multiply the oxidation part of the reaction by 5 and the reduction part of the reaction by 2. 5 into 2, 10 FeSO4 gives 5 into 1, 5 Fe2SO4 thrice. 2 into 1, 2 KMnO4 gives 2 into 1, 2 MnSO4. So now the equation becomes 10 FeSO4 plus 2 KMnO4 plus H2SO4 gives 5 Fe2SO4 thrice plus 2 MnSO4 plus K2SO4 plus H2O. In step 4, let us balance the other elements except hydrogen and oxygen atoms. What are all the other elements present in this reaction? Sulfur and potassium. In this case, potassium is automatically balanced because you could see 2 potassium in the reactant side and 2 potassium in the product side. Now coming to sulfur, in the reactant side we have 10 sulfur in ferrous sulfate and 1 sulfur in sulfuric acid. So totally we have 11 sulfur in the reactant side. Coming to the product side, let us count the number of sulfur in ferric sulfate. Here this 3 is common to sulfur and oxygen, right? So and this 5 is common to all the elements present in ferric sulfate, right? So 5 into 3, totally we have 15 sulfur in ferric sulfate. Coming to manganese sulfate, this 2 is common to all the elements present in manganese sulfate. So we have 2 sulfur in manganese sulfate and we have 1 sulfur in potassium sulfate. So totally we have 18 sulfur in the product side. Now let us balance the number of sulfur on both sides of the reaction. We need 8 sulfur in the reactant side to balance the number of sulfur atoms on both sides of the reaction. So let us multiply this sulfur in sulfuric acid by 8. So the equation becomes 10 FeSO4 plus 2 KMnO4 plus 8 H2SO4 gives 5 Fe2SO4 thrice plus 2 MnSO4 plus K2SO4 plus H2O. In step 5, let us balance hydrogen and oxygen atoms. Here we have 8 H2SO4. So to calculate the number of hydrogen atom, we have to multiply the coefficient 8 with its subscript 2. So 8 into 2, totally we have 16 hydrogen in the reactant side and 2 hydrogen in the product side. To balance the number of hydrogen atoms on both sides of the reaction, let us multiply the water molecule by 8 and the equation becomes 10 FeSO4 plus 2 KMnO4 plus 8 H2SO4 gives 5 Fe2SO4 thrice plus 2 MnSO4 plus K2SO4 plus 8 H2O. Now the number of hydrogen atom on both sides of the reaction is balanced. When you calculate the number of oxygen atom present in the reactant side and the product side, the oxygen atom is automatically balanced and this is the balanced equation. In this way, we need to balance the redox reaction using oxidation number method. In step 1, to balance the redox reaction using ion-electron method, we need to use the oxidation number concept and find out the reactants which undergo oxidation and reduction. Consider the same reaction, that is the reaction between ferrous sulfate and potassium permanganate in acid medium. Here Fe2 plus in FeSO4 loses one electron and becomes Fe3 plus in Fe2SO4 thrice. Since there is an increase in the oxidation number, this is the oxidation part of the redox reaction. Coming to KMnO4, Mn7 plus in KMnO4 gains 5 electron and become Mn2 plus in MnSO4. Since there is an decrease in the oxidation number, this is the reduction part of the redox reaction. So the ionic form of this reaction is MnO4, in which Mn is plus 7 plus Fe2 plus H plus gives Mn plus 2 plus Fe3 plus H2O. Here Mn plus 7 in MnO4 minus reduced to Mn2 plus and Fe plus 2 oxidized to Fe plus 3. This H plus ion indicates this reaction takes place in the acid medium. So we get H2O in the product side. In step 2, let us write the two separate half equations for oxidation and reduction reaction. The two half reactions are Fe plus 2 gives Fe plus 3 plus 1 electron and MnO4 minus plus 5 electron gives Mn plus 2. Since Fe plus 2 ion loses 1 electron, we write 1 electron in the right hand side of the reaction, and MnO4 minus ion gains 5 electron, we write 5 electrons in the left hand side of the reaction. While balancing the atoms and charges on both sides of the half reaction, there is no change in equation 1. Coming to equation 2, we have 4 oxygen on the reactant side. To balance the number of oxygen atom, let us write the ionic form of the equation. MnO4 minus plus Fe2 plus H plus gives Mn plus 2 plus Fe3 plus water molecule. Now we can balance the number of oxygen atom from this ionic equation. So we can write MnO4 minus plus 5 electron plus H plus gives Mn2 plus water molecule. To balance the number of oxygen atom, we write coefficient 4 in front of water molecule. Now the number of oxygen atom is balanced. Coming to hydrogen atom, we have 8 hydrogen atom in the right hand side. So to balance the number of hydrogen atom, we can write the coefficient 8 in front of H plus ion. Now we get the balanced equation MnO4 minus plus 5 electron plus 8 H plus gives Mn plus 2 plus 4 water molecule, and this reaction can be represented as equation 3. In step 3, we need to equate both half reactions such that the number of electrons lost is equal to the number of electrons gained. An addition of two half reactions give the balanced equation represented by equation 6. So in this reaction that we have taken, it lost 1 electron during oxidation and it gains 5 electrons during reduction. So to equate the number of electrons in this reaction, we need to multiply equation 1 by 5 and equation 3 by 1. After multiplying that equation 1 by 5, we can represent that equation by equation 4, and after multiplying this equation 3 by 1, we can represent that equation by equation 5. When we multiply equation 1 by 5, it gives 5 Fe2 plus ion gives 5 Fe3 plus ion and 5 electron, which can be represented by equation 4. Now, when we multiply equation 3 by 1, we get MnO4 minus plus 5 electron plus 8H plus gives Mn plus 2 plus 4 water molecule, which can be represented by the equation 5. Now, let us add the equation 4 and 5. We have 5 electron in the right hand side in equation 4 and 5 electron in the left hand side in equation 5. So we can cross this 5 electron in equation 4, which is in the right hand side, and 5 electron in the left hand side, which is in the equation 5. Now, when we add 4 and 5, we get the final equation 5Fe2 plus MnO4 minus plus 8H plus ion in the left hand side and 5Fe3 plus Mn2 plus 4 water molecule in the right hand side. So equation 6 is the balanced redox equation. In this way, we can balance the redox reaction using ion-electron method. Students, let's recall the topics that we have discussed in this session. In this session, we have discussed two different types to balance redox reactions, and we have discussed how to formulate a balanced redox reaction from two half reactions. Students, so far we have discussed 14 sessions for this first chapter, some basic concepts of chemistry in grade 11. We have covered both Tamilnadu syllabus, that is S.C.E.R.T and N.C.E.R.T syllabus in these 14 sessions. Hope all these sessions were very useful to you. See you soon in the next chapter. Have a nice day. Thank you.